I would like to thank Patrick and Andre for your invitation. I'm very glad to share our recent work on the study of ISS for partial differential equations. And I would like to thank everyone for being here. Today, I will introduce how to establish global IS for the box equation with Dirichlet boundary disturbances. I will also introduce a new notion called the generalized Lyapunov functional. This is a joint work with Professor Gu Chuanzhu, and the details of calculations can be found into our papers. So this is the outline of the presentation. In section 1, I will introduce briefly the development of IS for PDEs and the box equation. In section 1, I will present the main result obtained in this work. In particular, I will present how to prove the IS in different norms for the box equation with different coefficient B. In section 3, I will introduce a new notion called the generalized ISS Lyapunov functional. We will show how to establish the ISS for general control system by using the so-called generalized ISS Lyapunov functional. Then I will provide some concluding remarks. I would like to mention that the notion of ISS was firstly introduced by Zheng in 1989. It was used to describe the influence of external inputs on the stability of finite dimensional nonlinear systems. I recommend the book written by Andrei Milchenko. In this book, comprehensive surveys on studying the ISS were provided. An overview of IS theory for partial differential equations and more general case has been also included in this book. As for the ISS for PDEs, the study started around 2008. A lot of people have obtained significant progress on the study of IS for PDEs with different disturbances. I just list some of them. I would like to mention a bit little about the application of ISS for PDEs. In fact, the ISS theory of PDEs can be applied to various of fields in the engineering. For example, the ISS of PDEs can be applied to the problem of multi-agent control and traffic flow control railway track model. In recent years, we have also applied the ISS of PDEs to the problem of aggregate power control. For the methods used for the stability of IS in PDEs, I would like to mention that the Lyapunov method can be applied to the PDEs with only in-domain disturbances. But for PDEs with boundary disturbances, the situation becomes more complicated. In general, it may be difficult to apply the Lyapunov method for the stability analysis for PDEs with different boundary disturbances. So at the beginning of studying the ISS for PDEs, some non-Lyapunov methods were proposed. For example, these methods can be applied to linear PDEs, and these methods can be used for nonlinear PDEs. But in some cases, the Lyapunov method is still suitable for the stability analysis. For example, for PDEs with Robin or Neumann boundary disturbances, the Lyapunov method can be applied directly for the stability analysis. In particular, for PDEs with Robin or Neumann boundary disturbances, coercive Lyapunov functional can be constructed. And for one-dimensional heat equation with Dirichlet boundary disturbances, some non-coercive Lyapunov functional can be also constructed. A few years ago, we have also applied the so-called approximation of Lyapunov functionals to establish ISS-like estimates for PDEs with different boundary disturbances. But in general, for PDEs with Dirichlet boundary disturbances, it's much more difficult to apply the classical Lyapunov method for the ISS analysis. I would like to mention one of our papers. In this paper, we have summarized the methods used for the stability analysis. Of course, I'd like to recommend the book written by Karafelis and Kritic. This is the first book that focuses on the study of IS for PDEs. Then I'd like to recommend two papers written by Milchenko and Pierre. In particular, in these two papers, some open questions were proposed. The Burgers equation that I will introduce today was raised several times in these two papers. So let's look at the results on the Burgers equation. We take this viscous Burgers equation as an example. Here F represents in-domain disturbance, and D0, D1 represent boundary disturbances, and B0, B1 represent boundary operators. So what do we know? In fact, for the Burgers equation with only in-domain disturbances, we can apply the Lyapunov method to establish global ISS and global integral ISS for this equation. When we consider the Robin or Neumann boundary disturbances, we can also apply the Lyapunov method to establish global ISS and global integral IS for the system. But for the Burgers equation with Dirichlet boundary disturbances, as aforementioned, it's difficult to apply the classical Lyapunov method to establish the global ISS estimate. But by using the so-called the George iteration, we can still prove that the system is local ISS and local integral ISS. A few years ago, we have also applied the approximation of Lyapunov functionals to establish ISS-like estimates for the Burgers equation. But in such a case, the estimates are given in weighted norms, so it is still a local property. It's not the real global ISS or global integral ISS estimate for the Burgers equation. Therefore, it is still an open question how to establish global ISS estimates for the Burgers equation with Dirichlet boundary disturbances. This question was proposed several times in the papers of Milchenko. So today I will show how to establish this global ISS for the Burgers equation. So for simplicity, we only consider the case without in-domain disturbance, although the proposed approach is suitable for the Burgers equation with in-domain disturbances. Here we consider the case of Dirichlet boundary conditions. Note that if B is strictly large enough, then the Burgers equation is unstable. So we would like to impose a condition on B first. That is to say, we assume that B is strictly less than pi squared over 4. We assume that the boundary disturbances belong to this space and the initial data belong to this space. And these assumptions, we can prove that the system admits a unique strong solution. Let's look at the definition of ISS for the Burgers equation. For any Q no less than 1, we say the system is globally ISS in a spatial LQ norm if there exist comparison functions beta and gamma 0, gamma 1 such that this estimate was true. Here, the class of KL and K are defined in a standard way. An important characteristic of a function in KL is that it is increasing with respect to its first variable, and it is decreasing with respect to second variable and tends to 0 when t tend to infinite. Here we take maximum between these three terms. Of course, this estimate is equivalent to this one. Here we take maximum between only two terms. Of course, they are both equivalent to this one. Here we take sum instead of maximum. In the following, I will different but equivalent ISS estimate in the considered problems. This is the main result obtained in this work. The first result says that if B is strictly less than pi squared over 4, then the system is ISS in the spatial infinite norm. When B becomes negative, then we can prove that the system is ISS in the spatial LQ norm for any Q no less than 2. Furthermore, if B becomes strictly negative, then the system is IS in the spatial LQ norm for any Q no less than 1. So I will show how to prove each result in this theorem. First, we consider the case of B strictly less than pi squared over 4. In fact, I would like to prove this estimate holds true. Here we take maximum between these three terms, and the constants C0, sigma 0 are dependent of the coefficient B. Because we intend to prove the global bound of the solution W, we would like to prove its upper bound, then prove its lower bound. Then, in the last step, we can combine these two bounds to obtain the global bound of W. So the main proof consists of three steps. This is the first step, and this is the second step, this is the last step. But note that the box equation may have a positive coefficient. So it's difficult to apply the Lyapunov argument for the stability analysis when B is positive. So we would like to make transformations to transform the original system into an equivalent one. Here the reaction coefficients B hat is strictly negative, and the coefficient of this nonlinear term is also strictly negative. In fact, this can be done easily because B is strictly less than pi squared over 4. Then we can find the constants C and sigma such that this inequality holds true. In particular, this quantity B hat is strictly negative. Then we can define the function beta by using the cosine function and define the transformation by this. Then we can obtain this system. Here B hat is strictly negative, and the coefficient of V squared is also strictly negative. So it can help us to deal with the reaction terms, but there are still boundary terms. So it's difficult to apply the Lyapunov method to estimate the boundary terms. To do so, we would like to use the so-called temperature truncation. In fact, because B hat is strictly less than 0, so we can find sufficiently large P such that the sum of them is strictly less than 0. Then we can define the truncation functions GS and capital GS. For these two functions, they are both differentiable, and they are both degenerate when S is less than 0. That to say, the function GS and capital GS are both positive semi-definite. Then we would like to define a constant Kc by using the maximum of three terms, that is the infinite norms of boundary disturbances and the initial data. By using these definitions, we find that Gv minus Kc equals 0 on the boundary of the domain, and it is also 0 at the initial time. In particular, this property can help us deal with the boundary terms when we use Lyapunov argument. In the Lyapunov argument, we would like to calculate the derivative of some functional. In fact, we calculate the derivative of this functional because capital G is positive semi-definite. So this functional is also positive semi-definite. By using integrating by parts, we can obtain this estimate. Here there are 6 terms, but for the first term, because of G V minus Kc is 0 on the boundary of the domain, so the boundary terms can be easily handled. In fact, it is 0. And for the second term, because P is strictly less than 1, so Gs is an increasing function with respect to S. So the derivative of G is positive. Then the second term is negative. So these 2 terms can be eliminated and only the sum of the 4 terms are left. But for these 4 terms, we can handle them easily. In fact, we can estimate the first term and the third term together. In fact, the sum of them is less than 0. There's no intrinsic difficulty to calculate this estimate. Here we only used integrating by parts and some properties of G. For the second and the fourth term, we can estimate that the second term can be controlled by using the first term. Then, combining these estimates, we can arrive at this differential inequality. That is to say, this functional is decreasing with respect to t. So we obtained this estimate. That is to say, the value of this functional at the time t is less than the value of the functional at the initial time. But at the initial time, we have that this term is 0. So we obtain that capital G V minus Kc is less than 0. That is to say, V is less than Kc. This implies that the solution has an upper bound, which is determined by these 3 terms. So we have completed the proof of the upper bound of the solution. Then we would like to prove the lower bound of the solution because the Berg's equation is a strongly nonlinear equation, so we will use another transformation to transform the original system into this one. Here, we still want to guarantee the positivity of reaction coefficients B tilde and this term. In fact, this can be done easily. We can find some constant C tilde and sigma tilde such that the B tilde is strictly less than 0. Then we can find some A tilde such that the sum of C tilde and A tilde is strictly less than pi squared over 2. Then we define beta tilde by using sign function. Then we can guarantee that the derivative of beta tilde is positive. Then this term is negative. Here, B tilde has been strictly negative. So in order to deal with boundary term, we defined G and capital G as before, and defined the constant Kc tilde by using the maximum of these 3 terms. Then in the Lyapunov arguments, we can derive that this differential inequality holds true. That is to say, this functional is bounded by using its value at the initial time, but at the initial time, due to the definitions of G and capital G and Kc tilde, we find that this term is 0. Then we obtain that V tilde is less than Kc tilde. That is to say, W has a lower bound, which is determined by the maximum of these 3 terms. So by combining the upper bound and the lower bound, we can obtain the global bound of the solution. That is to say, we can prove the system is ISS in the spatial infinite norms when B is strictly less than pi squared over 4. Now let's look at how to prove the IS in the spatial equinorm. for any q no less than 2 when b is negative. In fact, we can prove this estimate holds true. Here we take maximum between only 2 terms. Because b has been negative, there's no need to make transformations. So in the first step, we would like to define truncation functions first. In fact, for any p strictly larger than 1, we can define GS and capital GS like before. But we define the constant kc by using only the boundary disturbances. That is to say, we do not consider the initial data. We only use the L-equivalent norm of the boundary disturbances to define kc. This is the difference from the one in the last proof. Then, in the Lyapunov argument, we would like to calculate the derivative of this functional. Of course, by using integrating by parts, we can obtain this estimate. Here, we have only 4 terms, but for the boundary terms, they are 0 because of the properties of G and the definition of Kc. And it's easy to verify that this term is also 0. In fact, this can be done by using integrating by parts. And for the second term, we do not delete it directly, but use Poincare inequality to arrive at this estimate. And for the fourth term, we can calculate it directly to arrive at this estimate. In fact, we have to apply the properties of G and capital G. So we can derive that this differential equality holds true. Then, by using comparison principle or solving this differential equality directly, we can find that this functional has an exponential decay rate that is given by this estimate. From this to this one, we applied the properties of capital G. Similarly, we would like to calculate the derivative of the integral of capital G minus W minus Kc and obtain this differential inequality. So we can apply the exponential stability of this functional. Then, combining these two estimates, we can obtain that the functional of W can be controlled by this one. And we use properties of capital G again to obtain this estimate. This estimate is determined by the initial data and Kc. In fact, this estimate implies the ISS in the spatial LP plus 1 norm because P can be arbitrary constant. So we can conclude that the system is IS in the spatial LQ norm for any Q no less than 2. Here we can define Q by using the sum of P and 1. So we have completed the proof for the ISS when B is negative. Then we would like to show how to establish the IS for the box equation when B becomes strictly negative. In fact, we can prove that this estimate holds true for any Q no less than 1. Here, we take maximum between these 3 terms, and we have also take maximum between the 2 terms, and use the sum between the 2 long terms. Because we have proved the proof of IS in the spatial LQ norm for Q larger than 2. So it suffices to prove this estimate holds true for Q no less than 2. But in this case, the functions GS and capital GS are not differentiable because we set Q to be the sum of P and 1. In such a case, P is less than 1. So GS and capital GS defined earlier are not differentiable. So they cannot use for the stability analysis in the Lyapunov argument. To do so, we would like to construct some approximations of GS and capital GS. In fact, we can use a function rho epsilon s. Such a function was used several times in our papers and has many good properties. For example, it is C2 continuous, and the limit of rho epsilon s is s if s is not negative. So by using such kind of function, we can define approximations of GS and capital GS. In fact, we can define the approximations by G epsilon s and capital G epsilon s. For the two functions, they are both differentiable. In addition, they are both positive semi-definite. This is a graph of the epsilon s. It can be seen that when epsilon becomes smaller than the graph of the epsilon tends to the dashed line. This part is the graph of the function s. So we can use this function to construct an approximation of GS and capital GS and use G epsilon s and capital G epsilon s to the stability analysis. Then we define the constant Kc by using only the two terms and calculate the derivative of the integral of capital G epsilon. In fact, we can arrive at this differential inequality then by using the comparison principle to obtain this exponential stability of this functional. Then, by using the properties of capital G epsilon, we can arrive at this estimate. Here, there is a term corresponding to the L1 norm of the solution. But for any fixed time t, this term is a constant. And all the coefficients in other terms are independent of epsilon, so we can let epsilon tend to 0 and obtain this estimate. It is determined by the initial data and Kc. This implies the IS in the spatial LP plus 1 norm for the Brooks equation, because P can be chosen absolutely, and we can let P tend to 0 and 1. We can conclude that the system is IS in the spatial equinorm for any Q that belongs to the closed interval from 1 to 2. So let's make a brief summary on the proofs. In fact, there are 3 key points in the proofs. The first one is that we should construct some positive semi-definite functions GS and G epsilon s. This can be done by using the so-called Stamp-Bachar truncation. In the second point is that we should define a constant Kc. It may depend on initial data, but it should be dependent of boundary disturbances. These properties can help us deal with the Dirichlet boundary terms in the Lyapunov arguments. The third key point is that we should derive such kind of differential inequalities. Then we can apply the comparison principle to arrive the estimate of this functional or this functional. Then use the properties of capital G or capital G epsilon, we can arrive at the ISS in different norms for the Brooks equation. So what inspiration can we obtain from the proof? Is it possible to use some functionals that are positive, semi-definite, and depend on boundary disturbances for the stability analysis? I would like to say the answer is positive. So in the following, I would like to show how to extend the proposed approach to general case. In particular, I will introduce how to prove the ISS for general control system by introducing a new notion called the generalized ISS Lyapunov functional. But first, let's recall some basic concept of ISS Lyapunov functionals. First, we denote X, the state space of a control system, and the maximal U is the input set, and the sigma is a given control system. For simplicity, we assume that it is fold complete, and phi is a transition map. We assume also that the origin is an equilibrium point of the control system. This is the definition of ISS for an abstract control system. It can be defined in a standard way and can be found in many books and papers. I do not explain on it anymore. Let's recall the definition of ISS Lyapunov functional. Here, I would like to call it the classical ISS Lyapunov functional because we wanted to compare it with the introduced generalized IS Lyapunov functional in this presentation. We say a function V is a classical IS Lyapunov functional if there exist comparison functions such that this structural condition is fulfilled. Moreover, the derivative of the function should verify this implication condition. Then, based on the notion of IS Lyapunov functional, we can prove that if a control system admits a classical ISS Lyapunov functional, then it is ISS. Let me mention a bit little about these structural conditions. First, from the 16, we can say that if the function Vx is less than a constant m, then this term must be less than the constant m. This is the first point. The second point is that Vx is positive definite. This is because if x is not 0, then C2 is not 0, which is strictly positive. So Vx must be strictly positive. This is the second point. The third point is that V is not dependent of U. That is to say, we do not consider the influence of U when we construct Lyapunov functionals for the stability analysis. This may limit the choices of Lyapunov functionals when we assess the IS for some systems with external disturbances, in particular for PDEs with Dirichlet boundary disturbances. This is the facts I just mentioned. But from the proof of IS for the box equation, we can find that these conditions can be weakened. In particular, these two conditions can be weakened. For example, in the for the box equation, we can find some positive semi-definite function V given by the capital G, because G is positive semi-definite. So this functional is a positive definite semi-definite functional. And we can also consider functions depending on U. Here we denote by H1 and H2 and consider the composite functions V and H1 and V and H2 for the stability analysis. That is to say, in a general case, we may find some positive semi-definite functions V and H such that the composite functions V and H can be used for the stability analysis. So we would like to summarize the idea into a new notion called the generalized ISS Lyapunov functional. More specifically, we say a function V is a generalized IS Lyapunov functional if three conditions are fulfilled. For the first one, we replied the left-hand side of V in the classical condition definition with 0. That is to say, V can be positive semi-definite. The second one says that we can find some functions satisfying this structure condition such that this implication condition is fulfilled. This implication is in accordance with this one. Here we do not consider the inference of U, while when we consider the inference of U, this implication condition should be given in this form. The third condition says that we consider the derivative of the composite functions. In fact, we consider the derivative of the composite functions V and HR. This implication condition is accordance with this one. So if these three conditions are fulfilled, then we call the function V is a generalized ISS Lyapunov functional. By using this definition, we can say that a classical Lyapunov, classical ISS Lyapunov functional is also a generalized ISS Lyapunov functional. In fact, for a classical ISS Lyapunov functional V, we find H, which is given by X itself. So all these three conditions are fulfilled. So it must be a generalized ISS Lyapunov functional. Such kind of Lyapunov functional can be used for stability analysis for general control systems. Then I would like to show two special cases. One case is given by this. It says that if we can find some function space satisfying these three conditions, then such V is a generalized IS Lyapunov functional. In fact, in this case, the functions H we found is that H1 is given by X and H2 is given by minus X. If these conditions are fulfilled, then V is a generalized ISS Lyapunov functional. This functional can be used for the ISS for PDEs with in-domain or Robin or Neumann boundary disturbances. The second special case is given by this. If we can find some functions V satisfy these three conditions, then such V is also a generalized IS Lyapunov functional. Here, we would like to find a constant Kc, which is determined by the external input. In fact, in the definition of generalized IS Lyapunov functionals, the functions H1, H2 are given by X minus Kc and minus X minus Kc respectively. If we can find a function V satisfying these conditions, then we can use it to assess the IS for PDEs with in-domain or in-domain disturbance or Robin or Neumann or Dirichlet boundary disturbances. It's not difficult to verify that if the control system admits a generalized IS Lyapunov functional, then it must be ISS. The details can be found in two of our papers, and I will do not present the details here. In fact, it can be proved in a standard way. Let's look at the example. Here we take, we consider the nonlinear parabolic PDE defined over higher dimensional domain omega. Here F is an in-domain disturbance, and D is a Dirichlet boundary disturbance. What is the generalized IS Lyapunov functional for this system? In fact, based on the proof of IS for the Box equation, we can define the GS and capital GS as before. And we consider the state space given by LP plus 1 space. And this is the input set. This is for the input set. We defined VW by using the capital G. This functional is a positive semi-definite functional. Then we can verify all conditions in the case 2 are fulfilled. In particular, in the third condition of the case 2, we can define the constant Kc by using the sum of the boundary disturbances and in-domain disturbance, and verify that the derivative of this functional satisfy this differential inequality. So we can conclude that such kind of way is a generalized IS Lyapunov functional. Furthermore, we can conclude that the system is IS in the spatial equilibrium for any Q no less than 2. So in this presentation, we have introduced how to establish the global ISS in different norms for the box equation with Dirichlet boundary disturbances. There are 3 key points in the proofs when we use Lyapunov arguments. The first one is that we should define some truncation functions. They are all positive semi-definite functions. The second one is that we should define a constant that determined by the boundary disturbances. Sometimes it can be determined by the Dirichlet data. We have also introduced a new notion called the generalized IS Lyapunov functional and presented a generalized IS Lyapunov theorem. We have also provided an example to show what is the generalized IS Lyapunov functional for the parabolic PDE defined over higher dimensional domain. The main contribution of this work is to provide a new perspective for the stability analysis, in particular for the ISS analysis for PDEs with Dirichlet boundary disturbances. I would like to mention that the so-called generalized Lyapunov functionals can be also extended to other variations. For example, we can define the generalized integral input-to-state stability Lyapunov functional and the generalized input-to-state practical stability Lyapunov functionals. These concepts can be defined in a similar way. So in the future work, we would like to show how to construct generalized Lyapunov functionals for a wide class of partial differential equations and apply the generalized Lyapunov method for stability analysis for PDEs arising in engineering. So that's my presentation. That's all. Thank you. I'm looking for your questions.